Well, thank you very much. It's a very, very kind introduction. It's really a pleasure to be here and present to to FAST and a lot of storage experts here. And it's really fantastic. We'd love to hear your thoughts. Looking forward to your questions. And just a quick background here. We got started. We're both computer architects, and we've been fascinated by molecular biology for a while as a source of device technology to build future computers. So, and we started learning about molecular biology almost a decade ago now, maybe more. But this became more serious for us about 5 years or so ago when we formed the Molecular Information Systems Lab, which is a group of interdisciplinary researchers that do work in computer architecture, coding theory, molecular biology, machine learning, mechanical engineering, and so on. So it's really, we're here representing that group.
Yeah, it's a real pleasure to be here today. And yeah, I just wanted to add that the collaboration between Microsoft and University of Washington has been quite a productive collaboration as well. All right, so let me start with the problem. The DNA data storage project is our flagship project right now at the MISO. And so let me start with the problem we saw as we started the project. So what you see here is years on the x-axis and number of bytes on the y-axis. And as is no news to this community, we are capable of generating lots of bytes, but we're not as capable as storing the bytes. The devices that store information are not growing as quickly as the data we generate. And so there's a gap. And obviously, we don't need to store all the information that we generate, but we want to store a portion of that information. And the issue we're seeing is that the data that we can store versus all the data that we generate is shrinking. And so we have to discard a larger portion of the data. So that's sort of the problem here. So to put a dent on this problem, we thought that we should look at radical new solutions to it, and DNA data storage is we think is one of them. So to contrast that to the status quo, I just wanted to do an analogy here, comparing, Moore's law, which we're all familiar and learn to love, where we have devices, we make them smaller, we pack more of them in a particular chip or device, and then we continue that improvement, and that's how we've been getting gains in capacity in many of our semiconductor devices right now. Up to now. Now I want to contrast that approach with an approach that was proposed by Feynman back in the 50s, where he said that if we have the ability to arrange atoms in the way we want, then we would be able to create nanoscale computing and storage devices. And in fact, he even used DNA as a molecules as an example of data storage. At the time, he used it as a genetic data storage type of material. However, and he didn't really point out that you could store digital data in DNA. However, only a few years later, somebody came in and said, "Hey, we should really store digital data in DNA." And so that's sort of the principle here. So let's see, what does that mean to store data in DNA? So let's start with the basics. DNA is that double helix that we think of. Each side of the double helix is a sequence of 4 bases, A, C, G, and T that you're seeing there on the screen. And so if we want to store a sequence of bits in DNA, what we have to do is essentially to translate that, to use a simple mapping like what's on the slide there. 0, 0 becomes A, 0, 1 becomes C, and so forth and so on, to represent that sequence of bits. In reality, the schemes that we use are more sophisticated than this, but this is sort of an illustration. So we have an arbitrary sequence of bits. We transform that into an arbitrary sequence of bases, and then we have the ability today to put together the sequences of DNA of these bases in arbitrary ways. So we store data in synthetic DNA strands. That means we're fabricating those sequences of DNA. So there's no biology here. There's no life, no cell, no organism here. We're just using the DNA as the medium itself, as the material that we're stringing together to create molecules that represent the bits that we want to store. Now, why would we want to do that? First is reason is density. So what you're seeing here is a test tube with some DNA at the bottom. You see that's the pink smear. You see at the bottom is dried DNA with something that conserves the DNA, that preserves the DNA. And that little amount of DNA, that little volume of DNA is the equivalent of 10 terabytes of data. So you could store 10 terabytes in that volume. And to put that into perspective, here's a data center. Typically, cold storage data centers can house about 1 exabyte of data. DNA is best suited to cold storage. So if we were to scale DNA to this picture here of the data center, with that density that I showed in the previous slide, this is what it would look like. And you can barely see it, but it's there. It's really a pixel. And in real size, it fits in the palm of your hand, right? So super dense, 1 exabyte of data. One other property of DNA that we like is DNA, if kept under the right conditions, can last for a long time. So we know that there's evidence in the wild of DNA. I think last week or the week before, scientists have published having been able to decode DNA that was 1 million years old and that had been in the wild. And likewise, we don't need to use natural processes. We can use synthetic fossils, meaning using chemistry, synthetic chemistry, to preserve the DNA and preserve it for a really long time. In fact, collaborators from ETH Zurich have shown that DNA preserved synthetically can last for thousands to millions of years, depending on the temperature. And the other good news is that because of its density, creating the right conditions for DNA to be preserved for a long time is actually pretty easy. You could fit something like 32 zettabytes of information in the size of a freezer. All right, so that begs the question, how does that compare with media that we have today? So this is a plot where we showed where we are today with commercial media and where we think the projections of these media are going to get to in terms of density. So here on the y-axis, we have gigabits per cubic millimeter, so essentially bits per volume, right? And we show the different technologies. For DNA specifically, we're showing the limit, meaning the maximum theoretical limit, but obviously, if you're going to build a system that uses DNA as a medium, there's a bunch of overheads, but even if you discount the overheads, which is the top part of the bar there, and discounting that, we still get a few orders of magnitude improvement in density compared to other medium. Now, the next property that we like about DNA is that now that we know how to read DNA, we'll always be able to read it. So the media is not going to change. The technology to read it may improve, and in fact, here I'm showing the evolution over the next few decades. But the medium itself doesn't change. So we don't have that issue with obsolescence that we may have had with other types of media where, a floppy disk, who can find a floppy drive these days to read them? So with DNA, there will always be readers around. All right, another property of DNA that we really like is the ability to make copies and to make them in a pretty efficient way. So this is how this works. So what we're seeing here is a piece of DNA, and on top of it, there's a smaller piece of DNA that binds to it. So if you remember in the double helix, G's on one side bind to C's and A's on one side bind to T's. So this short sequence of DNA binds to the beginning of the longer sequence, and then an enzyme comes along and makes a copy of it. And this process repeats. We use heat to separate the two sides of the DNA, and then the process repeats. And because each cycle of it separates two of these pieces of DNA and makes two new molecules, the process is exponential. So very quickly, we can get tons of copy of the same DNA molecule. Um, and finally, another nice surprise that we had in doing the project is we did an estimate of a life cycle of DNA compared to other types of media, and to try to understand its environmental impacts. And we found that DNA looks very promising. And so both for greenhouse gas emissions, and so carbon emissions, energy consumption, and water consumption, DNA can provide a gain, at least based on our preliminary estimates, of about 2.5 to 3 times improvement to store 1 terabyte for a year. Now, if we're thinking about cold storage and we're thinking about preserving the information longer, this benefit only improves because there's no need to copy the information to a new medium every time that the old medium gets outdated, and DNA can be preserved for a long time. And so the longer period you store the information in DNA, the better the advantage compared to commercial storage solutions right now. All right, so this is what DNA data storage system looks like. So as I showed in the previous slide, in one of the previous slides, we start with bits. We translate those into sequences of the 4 bases that we have available to make the molecules. This is still in the electronic domain. So we have an encoder system that will come in and do that. And then we make those sequences into the actual molecules of DNA. Those molecules, and for storage, they're put away, they're preserved. And then when it's time to read, we'll perform random, and then sequence the DNA, which is the process that we use to read it. We get electronic representations of the molecules again, and we decode that into the original bits. So this all kind of sounds like science fiction, but it turns out we have stored over 1 gigabyte of data in DNA and have fully recovered the information in it. And to essentially, we wanted to make the point that if you can store it in bits, you can store it in DNA. So we picked different formats, all the way from text to high definition video to archival quality music, and stored it in DNA. And in storage, it doesn't sound like a big deal, but in biotechnology, this was actually a big milestone. So much so that we ended up on the cover of Nature Biotechnology. And every storage technology had to go through the 1 gigabyte milestone to get to full deployment, right, and to large scale. All right, so let me walk you through this process of storing data in DNA in more detail. So we start with encoding. So let's see, we want to store that OKGo video that I showed in a previous line. So it's a high definition video. It's short, it's about 44 megabytes of information. But the sequences of DNA we use to store the information, they're shorter. I showed in a previous slide that there are 150 to 300 bases long. That gives us about 15 to 30 bytes of information to store. So first step in all this, when we want to store something that's bigger than 15 bytes, is to chop up the bits that we want to store into smaller pieces. And this is not unlike what we used to do when floppies couldn't store, a whole image of a program we wanted to install. We add sequence numbers to them so that we can reorder them on the way out. We add some redundant data for error correction later. And then we transform those bits into sequences of DNA, and we add tags to them. So the lighter blue sequences that I added at the ends there they work as sort of an object ID. Okay, so now we know which sequences we want to produce. So the next step is to actually fabricate the molecules. And this is done by a process called DNA synthesis. And so the way it works is we build the molecules sort of base by base, and they grow from a surface, kind of like lawn grows from the ground up. And so each of these cycles that I'm showing here is adding a single base. So the way it works is, there's an A that's already attached. We want to attach a C next. So we flow a fluid that has a lot of C's in it, and one of the C's attaches to the A. Now, what prevents more C's from attaching to this C that just attached is this little hat that we have there. That's a chemical group that prevents any more additions. So we can add one base at a time and selectively. The next step is oxidation, just strengthens the bond between the two bases. And finally, when we're ready to add the next base to that sequence, we remove that little hat, the blocking group, and then repeat the process. And so there's a bunch of cycles of chemicals coming in and out to make DNA synthesis happen. Now, I'm showing here a single sequence. Obviously, we don't do one sequence at a time. We do it in parallel. That's a technique called array synthesis. And what I'm showing here is that the different colors of squiggles that I have there represent different sequences of DNA. So we can make different sequences of DNA all in parallel, but also we make multiple copies of it. So we get some redundancy for free also from the synthesis process. All right, so we made our DNA. The next step is to remove the DNA from that substrate where it was created and to encapsulate it. I'm showing here an example of encapsulation. This is based on silicon dioxide, so essentially glass nanoparticles. Those particles, the spheres that you're seeing in the picture are nanoscale, about 100 to 200 nanometers in size. We'll dry them and then we'll deposit them. Well, we'll deposit them in a DNA library and they're dried in that library. So this is not unlike a tape library, which is what I'm showing in the bottom here, is essentially a way to organize the data spatially so that when we want to retrieve it, we can easily find it. Now, when we're ready to read the DNA, we'll retrieve the molecules. Now, within each of these pools in the library, each of the red dots or each of the dots you're seeing in the library, there may be multiple files. And so it turns out that the process of copying that I explained before can actually help us extract files, do random access over files. It's sort of a chemical random access, if you will. So within that one dot in the library, there are multiple files. We want to extract fewer files than there are there. Maybe we're interested in accessing one picture out of a collection. So let me show you how we do that. Here are the two sequences on the screen represent two different files. So let's say the dark gray file and the light gray file. And let's say we only want the light gray file. So what we can do is we add the sequence corresponding to the object ID or the file ID only for the light gray file. And then enzymes will come in and they'll do the copy. So they copy a lot more the light gray file because there's that matching in the beginning than the other file where there's no matching double helix in it. And so we can make very quickly, we can make copies of the light gray file. And then when you sample from this, the probability of grabbing mostly sequences from the light gray file is much higher. And that's how we're doing chemical random access in addition to the physical random access that I explained in the previous slide. All right, so the next step is to sequence. So we're reading these molecules. The way there's multiple ways to read the molecules. Here I'm showing a sequencer by a company called Illumina, and the process to read it is optical. So again, we're going to use that property that A binds to C and to T and C binds to G to essentially tell what molecules are in the sequencer. So here, for example, we have a T that's attached to something that glows green. And that T, because we have an A in the sequence to be read, it attaches to that A. And then we can see that there's something green there. Next step is we remove the green, we attach a new base. This time it's a G, and the G is characterized by a more yellowish color. We can see that there's a G there, and so forth and so on. And so what this machine gives us is a bunch of sequences of DNA. So this is back into the electronic domain. It's a bunch of sequences of DNA, but you see the bold letters there are errors. So this process is not 100% perfect. There are error rates, and I'm going to show them in a second, but just to essentially say that what we're getting out of the reader is a noisy representation of the molecules. Here's another way to read the information. This is an emerging technology. It's called nanopore sequencing technology. And the principle here is you run the molecules that you want to read through this nanopore. What looks like a champagne cork right there is what's called the nanopore. It's a pretty narrow channel. The DNA goes through it, and as it goes through it, we measure the current disturbances that DNA is creating. And this is what you see here in the middle is a current trace where we can tell which of the different 4 bases are going through the nanopore. This is an emerging technology. There is even more sources of noise, so we get even noisier representations of the molecules that we think are in the mix. So just to give you a sense of error rates, this is sort of a comparison of the types of errors. And so it turns out for DNA, there's different types of errors, insertions, substitution. So it's kind of like the type of error you see in networks, where symbols may disappear or may be inserted, but also substituted, just like we're used to in storage. So we're showing the 3 types, and you see the bottom one is a lot noisier. However, despite all this noise, we can actually recover all the bits. So let me show you how we do it. First step is we take all the sequences we got from the reader. We call them reads. We organize them so that we group them. We're essentially clustering them in clusters that each group is a group of reads that are likely to have come from the same location in the file. So you see the darker blue here is showing an address, and so those are grouped. Once we have the groups within a group, we'll do majority voting so that we can recover the most likely sequence that was put in, right? And once we have these sequences, we can then recover the bits that we had stored with their sequence number so that we can put them all together and recover the information. Now, there's another type of error that happens here, which is sometimes we don't recover the information for certain positions. Now, we had initially added redundancy. This could be a Reed-Solomon code. It could be a DPC code. And so we use that redundancy that we had added in the beginning to recover from erasures that may happen in the process. The important thing here is that there's no single sequence that's crucial. As long as you get enough sequences back, you can recover the bits. So once we recover the bits with their sequence numbers, we essentially reorder them and then recover the original file. So in a nutshell, that's a very quick overview of how we put together the system. And now Luis is gonna take over. He's gonna talk about trends, computing in DNA, and future opportunities.
Great. All right, thank you very much. It was fun to answer the Slack thread real time while Karin was speaking. So also just to say like how real this is becoming. So there's this DNA Storage Alliance that was announced recently that includes a lot of the core storage companies like Western Digital and a lot of molecular biology companies like Illumina and Twist Bioscience and so on. So let me talk a little bit about the trend of improvements here. So this is a paper that we put together a year or so ago on how fast DNA data storage is progressing. There's a paper in Nature Genetics Reviews that shows on the y-axis the total amount of data that was stored in DNA in log scale, and then the x-axis the year. And note that the first demonstration was actually pretty early on. Davis actually stored data in DNA and read it via gel, which is those bands that you see in forensics movies. And it was a very fast improvement. And this is a line here that you see that after you went from column synthesis, which means making a molecule at a time, to making a race synthesis, which was Karin talked about, like making a bunch of those in parallel. We are at gigabyte scale now, and in fact, you're going to see some outcomes and results of major investments from the U.S. government and industry in pushing this even faster. So the progress has been really, really tremendous. So let me talk a little bit about some of the things that encourage us to think about the trends here. The first one is called Carlson curves. It's essentially like Moore's law for molecular biology, where Rob Carlson, who actually happens to work with us, he consults in our lab. It shows the progress in DNA writing and reading over time. This is throughput also improving exponentially. And for reference here, the solid dark blue line here is Moore's law, and the light blue dots here is actually progress in DNA reading. And while writing is lagging a bit, because of the data storage, there's been an uptick that you're probably going to see updated soon. So that's throughput. But now let's talk about latency. And I know there were some questions in the Slack already on where does it fit in the stack. Well, the latency here is likely to be high. Think minutes, probably hours. So similar SLA that you'd have for very cold storage, like Glacier, where you talk about hours, maybe half a day to go pick up a tape or a hard drive stocked somewhere. We're talking about the level of latency is about the same here. Now, there are technologies that actually, from the read side, potentially could bring it to real time. So nanopores could have latencies on the order potentially of micro or milliseconds. That could change the story, but I think that's fair to say that most likely this is going to be more applicable for batch storage and archive. Okay, so let me talk a little bit about what are some trade-offs that we could play in trading off accuracy or the accuracy of reading and writing and the type of molecules that we make to trade off for higher throughput and lower cost. So let's talk about errors first. So DNA synthesis is used for life sciences. That's why it was invented, right? You print DNA to put inside a cell to potentially modify its behavior. But in life, it turns out that if you make a critical error in a single base, it could cause a very serious mutation. So life did the way we build computers. Okay, so in computers we build codes in a way that it doesn't matter. No bits, typically no bits more important than others, and that's how we build the codes in DNA data storage. In fact, in data storage, we can tolerate insertions, substitutions, and deletions in an arbitrary way, depending on the level of redundancy and the type of coding that you use. So in data storage, it's much more tolerant to errors than DNA synthesis for life sciences. That's why it gives an opportunity to explore this trade-off of trading off accuracy for better throughput. The other thing that's important to keep in mind is the size of the sequences. As Karin talked about, the block size for us, is on the order of 150, say 200 bases each molecule, and think of it as roughly 250 bits, a payload of about say 10, 15 bytes. The rest is metadata, and we stop there. Yes, we can increase the length, but then the metadata grows logarithmically, and the payload keeps growing linearly with the size of the block. That means after a while, it doesn't make sense to make it much longer because you get diminishing returns in terms of reducing overhead. So therefore, there's a sweet spot on the order of a few hundred bases. That's where we are today. The good news is that we can do that very fast, and that's how DNA synthesis works pretty well today, is to make lots of little sequences of a couple hundred bases. And the good news as well is that since it's so short, it's unlikely to actually code for any meaningful protein, making it inherently generally safe, for use in synthetic cases. That's why people even use DNA to tag materials, and so it's something that we're going to talk about in a bit. So, okay. Now, let me talk a little bit about something very exciting that I think has an opportunity to, bring yet another dimension of excitement and possibilities in DNA data storage and molecular systems in general, which is bringing compute. Okay, to put this in perspective, this is the flow that you saw before. After encoding, and we go to the molecular domain with synthesis. this is in the molecular world here. And at that point, like assuming a single say solution, right? A single vessel, you have a bunch of molecules floating around, um, or they're dehydrated in the surface. But they have um, very high parallelism in how they interact with each other. You know, you can actually do operations with very low energy on a per molecule basis. And it turns out that if you can do computing in that domain, you have a lot of bandwidth and energetic advantages. And you might want to do that before converting it to electronics, because there's a bandwidth limitation here between the molecular and the electronic world that, you know, even though it's improving fast, it's likely that you're going to suffer from capacity over bandwidth ratio. So I'm going to tell you some examples, or one key example that we're working on that. So uh, but for that, let me bring you back briefly, super high level. You probably heard of DNA computing. Len Edelman was a very famous computer scientist. Have done a bunch of things, including cryptography, right, and you know a bunch of in parallel computing and so on. In the 80s, he came up with this idea of actually using DNA to solve a computing problem. Well, this is the first demonstration of DNA computing. And the problem that he was solving is solving a Hamiltonian path problem, which is essentially you have a bunch of dots, you have a graph, and what you want to do is you want to come up with a path that visits all nodes. Okay. So the way he did that is by encoding that in DNA in the following way. So for each node, he encoded in DNA and made a molecule, a sequence that corresponds to that node. So these are two different nodes, node one and node two. For every edge, he designed the coding such that if this edge connects two nodes, part of one edge physically attaches to the molecule for node one and physically attaches the molecule to node two. So with that, once you synthesize the DNA for all nodes and for all edges, you mix it in test tube, you shake it, put in the right temperature. Eventually, this converges into a long molecule that if it's long enough to visit all nodes, you found a solution. Okay, that's really cool, super important demonstration. Except that it's a demonstration. It's unlikely to be practical because for any meaningfully large problem, you need an exponential number of molecules, right? Because you know, as you grow the number of nodes, number of edges will grow exponentially, and the amount of material you need to solve the problem is going to grow exponentially as well. So not the number of edges, but the total number of possible solutions would grow exponentially. So you shift complexity from exponential time to exponential material, which makes it impractical. So that's why we like to think about DNA computing today in a different way. So we think of DNA computing in the age of big data, which means that we're not interested in solving problems that are in exponential time in nature, like Edelman was looking at. I'm interested in solving um, problems that are polynomial time in the amount of data. Okay. And we wanted to find ways of operating on data that's stored in DNA directly instead of having to convert back into electronics, because that makes it extremely parallel and energy efficient. Okay, so the problem that we went after is content-based image and video search. I know that this community looks at that, right? So essentially the key idea here is you have a database of images, you have a query image, and you want to find, say you have an airplane, you know, search for everything that looks like airplanes in your database. So we're going to do that in DNA. So how are we going to do that? Well, remember that DNA sticks, okay? So if you have a fully complementary pieces of DNA, meaning that all bases match to all bases on the other hybridized all bases on the other molecule, you form a very so this is a perfect complete match. That's what you have in double-stranded DNA in your chromosomes, by the way. So both sides here. So A binds to T, C binds to G. So that binds very, very strongly, makes the molecule strong. Now, even if you have partial matches, you still bind. You have even poorly partial match, you still bind as long as you have enough of them. So I hope you see where this is going now. You can actually use the probability of attachment, the strength in which they attach, as a metric of distance between two sequences. Okay. So that's how we build essentially a search engine in DNA. So what we're going to do is something like this. Okay. So you have a database with a bunch of things that you're searching for encoded in DNA. And then you're going to encode your query as a complementary piece of DNA that's attached to a magnetic nanoparticle, tiny little particle that you can extract with a magnet. Okay. So now what you're going to do is after you mix that in, things that have really good match come out with much higher probability. Okay, because a lot of them are going to attach to the query. The ones that are less good of a match, either they're not going to attach at all, or they might attach with very low probability. So now let's turn that into a search engine for images. So this is a paper that we had a paper a couple of years ago that laid out the early foundation for that idea, and now there's a bigger paper on bioarchive that you can search for. So here's the key idea. The key idea is to train a neural network that can map the visual features of an image into DNA sequences, such that if the features are similar in the feature domain, the corresponding DNA sequences that encode those features are more likely to bind to each other according to the rule that we just talked about, or the hybridization rule. For example, we have two binoculars here. So this is our database. This is our features for the query. That's another binocular. So we're going to encode this in a way such that the probability of binding to the binocular will be much higher. Okay. So that's really the key idea. So the molecular mechanisms here are very well understood. Life uses it all the time. Molecular biologists use this all the time. So you can use this for search engine for searching, as long as you can encode it in a meaningful way. All right, so let me give you a quick demo. Suppose that you have your query here. Okay, so now those are the features of your query. And now we design this hash table in DNA such that part of the DNA molecule encodes the features and the other part encodes an ID. Okay, so features to ID, typical hash table. Okay, so now, sorry, that was your database. Now the query is going to contain only the features that you're looking for. And if they're similar enough, they're going to attach. And because they have a magnetic nanoparticle, here you can actually physically extract this with a magnet. Okay, sounds crazy, but it actually works. So now let's put this all together. Here's our database with all the different images. Here's the images that the query that you're searching for, replicated a large number of times, attached to the magnetic beads. You're gonna mix it all in a big soup. Whatever is similar enough attaches. Okay, whatever is similar enough attaches, and then with a magnet, you can extract all the molecules that came with it, and then whatever. And that's really the picture here on the top left. That's the picture. That's the picture that shows the dark part there. That's the magnetic nanoparticles, and the DNA is attached to that. Okay. So once you take that out from solution, you take the molecules that are attached to it, and then when you sequence them, you have what you're looking for. You're probably thinking this is completely nuts, this is crazy, right? No, it actually works. Okay, and the key idea behind this is actually um, not unknown. If you've heard of semantic hashing, where you map a high dimensional space, in Euclidean space, say, to a binary space, that you can actually just use population count, XOR and population counts to essentially using Hamming distance. We do this all the time in machine learning. We're doing that the same, except of translating from image features into binary sequences. We translate from uh, image features to DNA sequences, and we have a way of determining the similarity, like I just talked about. Let me go fast here, but basically the training loop looks roughly the following way, right? So we have, for every pair of images that we're training, we're going to train a encoder such that the distance measured by a predictor of how likely is it that the molecules are going to bind has to agree with the entropy loss. And we do cross entropy loss, has to agree with the difference with the distance in the corresponding image features. Okay. Let me just skip this. This is like more details on the neural network. So does this work? Yes. So these are the results. Okay. So what I'm showing here is some experiments that we've done. We've encoded 1.6 million images into DNA sequences, put in a test tube, encoded the queries into the DNA sequence that is attached to the magnetic nanoparticle. We extracted it and we read it with an Illumina. And what this is showing is two queries. On the left here, in the bottom left, is searching for the binoculars. And on the x-axis, we show the Euclidean distance of the corresponding images. And the y-axis is the molecules that appeared in the sequencing post magic molecular and things that have low distance, the things on the left, appear more frequently, which is exactly what we want. Okay, can go into more detail later. I just thought I'll flash these results. It should actually demonstrate this in the wet lab. Now, putting my computer architecture hat, why am I excited about this? And This is where I think it's gonna get even closer to your world. Like I'm sure have all observed that the time it takes to read the whole hard drive, say, over time increases because capacity of a hard drive grows faster than the bandwidth. Okay, this is actually true in 3D, physically 3D organized storage, because you could think of the capacity of a storage device to be proportional to the volume of these 3D objects, and the bandwidth be proportional to the area of the surface, because that's where the wires or your magnetic head will touch and so on. Or even if you're talking about optics, that's a surface in which you can actually go and read things that are inside. Okay. So if capacity grows with the cube and bandwidth grows with the square, it means that you're always increasing capacity over bandwidth. It's always going to take longer to read larger storage devices. Okay. So now you've all heard of near data processing. That's happening in computer architecture today, where you put processing very close to storage, either secondary storage, and we're putting close to flash, or in main memory, if you're putting close to DRAM or even SRAM. We're doing this to increase bandwidth, right? So when you actually, this is a way of breaking this capacity to bandwidth ratio. Well, if you store data in molecular form, remember that you're not putting all of this in a physical 3D structure. This thing's floating solution. There is no well-defined 3D, macro 3D structure. So you can imagine your compute element diffusing through your data. So you're not limited by the typical bandwidth that is associated to the capacitive bandwidth associated with your device when you physically manufacture it. So I find this very exciting because now you have this opportunity to think of these compute engines that diffuse through the data and get as much bandwidth as there are computing elements to read them. Okay, so it's going to be at a higher latency, but you have much higher bandwidth. Okay, so I talked about one vision for computing for near molecule processing, right? So that's why I really think of this as, just to go back to this, you have physically close compute engines to the piece of data encoded in molecular form, except that the ratios are extreme. Think of it as tens or hundreds of bytes, and you have a tiny little compute element just gets physically close to it and bump into each other to interact and do the computing. Okay. So, all right, we talked about all of this. So here's a vision that we have on building a DNA data storage system with potentially integrated processing: is to have, stations, rack size stations that you do write, we store them away, and then you read them. This is the vision, make it fully automated. The reality today is largely like this. This is a picture in our lab that we have people with pipettes, moving around. This is Lee Organic, one of our grad students, and me there pretending to be useful. um, and she's actually manipulating synthetic DNA. So there's a lot of manual work going on, and we are striving for full automation, just like large scale molecular biology and wet lab automation is going. We're going to do that for DNA data storage and molecular computing, but to an extreme. So we actually built a device a couple of years ago. It was the first demonstration making a fully automated engine that converts bits to molecule back to the sequencer and back to bits, and built this in the lab to see what would it take. So this is the synthesis side. You see the bottles of A, C, Gs, and Ts there. You see all the tiny little tubes that actually mix them to synthesize them. So in the middle there, you see the storage and synthesis and where the molecules are actually stored. And on the right side, you see sequencing, and that's a nanopore device that you see right there with the blue plastic cap, right? So with the blue thing on top. So that's you see the tube going inside. I don't have a pointer here to show you, but okay. Now this is also very far away from this, right? So this is a fully automated retrieval system. So now we're actually extending this with what we call digital microfluidics. Think of it as shrinking the ability to manipulate small amounts of volumes in a very well-defined way that's controlled digitally. So let me give you an example. Okay, so this is a digital microfluidic system, and the way that works is you have in a grid of electrodes and a piece of conductive glass on the top. As you apply voltage in each one of these electrodes, kind of like the way you apply voltage to a display, you can make the droplet move. Okay, so and that's it. So that's a movement. And here, let me show you some examples, so some videos. So Can you guys see this? Hope you can see the droplet moving. This is being controlled by a Python script, and we have on top here a camera that is monitoring where the droplets are to actually do closed loop control and error correction. So these are the computer vision identifying where the droplets are. And that's what we use to actually pick up DNA material from one position and put it in another position. So for example, this is how we built our library storage system. And what I'm showing here is this piece of glass on top has a bunch of spots of DNA. Think of it as large pools, each one of them at about terabytes. And then a droplet can go and visit it, soak the DNA that's there, and then take it to the sequencer. Okay, so let's think of it as really as liquid robotic arms that goes and picks up with the equivalent of a tape and sends it to the sequencer. And there's a paper there, Nature Communications, also a couple of years ago, that talks about how well that works. And we show that there's no contamination as they move around. And I thought it was cool to show you that we use these liquid robots as ways of moving information physically around. Okay, so okay, now we're actually building, there was an ASPOS paper a couple of years ago on a full hardware software stack that's fully open source on digital microfluidics, because we do see this as an opportunity to apply a lot of what we learn in computer systems, but to the fluidics and, wet lab automation world. So we built a hardware, it's called Purple Drop. There is a paper IEEE Micro last year that describes in detail. So the assembly code to program it is turn electrodes on and off to move the droplets. So we abstract that away actually with a language called Puddle that allows you to program this in Python, compile that down to all of the control signals to make the droplets move, and do the equivalent of what you have done in the wet lab with pipettes. We do that with this high-level Python script. Okay. So we see that as a general stack. By the way, we are very focused on molecular computing and storage. We're building it to automate that. But there's other uses that others are exploring of our platform. It's one of the beauty of these things that gets repurposed. And even though we're building for very large scale automation for the data storage, if we achieve that, that could be useful to do, say, global scale sample processing, which hint hint could be useful in something like when the whole world is stopped because of a tiny little molecule, right? So okay, so the way I think about this is that we've been building computer systems with hardware and software for a long time now. We do think that there's an opportunity to think about wetware here in the picture to control the interface between the molecular domain and the electronic domain. And this gets Karin and I as computer architects very excited about the computer architecture as we get more devices into the picture because of the following, right? We've been having specialized computing for a while now. We have CPUs, GPUs, accelerators, and reconfigurable logic like FPGAs built out of electronics, super low latency, highly engineerable, perfect control, and it's useful to do all the computing we do today. And we specialize in the architecture based on the algorithm. But now what if you could also specialize what you do with it based on the device technology behind it, right? So as we know, there's quite a bit of progress going on in quantum computing to do optimization type problems. It's massively parallel. Obviously, but very hard to get data in and out because you're talking about operating at gradients of temperature that goes from millikelvin codes all the way to room temperature where a lot of your data is. So that transition, limits a lot of the data bandwidth in and out of a quantum computer. So it's good for problems with little data, lots of computing, and little data out. Now, biomolecules is the opposite. It's lots of data. You can have massive bandwidth, but the compute primitives are likely to be very simple, massively parallel, and it wouldn't solve problems like what quantum systems solve most likely, and it wouldn't solve problems that you can solve in electronics. It would be good for things like you have a ton of data, you have say 100 trillion data items, find me the most similar one. This is a perfect problem to do in biology, in biomolecules, and not the right problem to do with computers because of, say, curse of dimensionality, right? And also probably not the right problem to solve with quantum because of the massive IO needs. So with that, I'd love to say thank you to Miso. This is a relatively old picture, but there's roughly 25 of us. It's highly interdisciplinary, and we are growing the lab. If you're interested in learning more about what we're doing, just go to miso.by or miso.ch.washington.edu or the Microsoft Data Storage Project to learn more about it. Okay, cool. With that, I will come back to this just to leave it as the final slide and take live questions. I think we have about 10 minutes, right?
Yeah, something like that. So thank you both. I couldn't keep up. I think that between the two of you, you've managed to answer most of the questions on Slack. And so let me start just with the two high-level questions that I have. Um, Speaking in front of the storage systems community, you know, we build file systems, object stores, we create software stacks for storage devices, define interfaces. What do we need to do to make your vision come true? The one with the data center of DNA storage.
I think it's a great question. So many ideas come to mind. I would say that first of all, think of ways of building archival storage systems with very deep hierarchies that would have that would keep enough metadata for you to do very usable, very flexible searches. Like, let's think about this. If we were to build a file system to store all the data in the world in a way that would be meaningful 100 years from now, how should you organize it? Right? So how should you organize information? I think it's a mix of not just the mechanics of the storage system, but also how do you think about information retrieval with advances in machine learning, for example, and so on. Just like this is one of them. Organizing large archives that's going to be meaningful for hundreds of years, right? So, and then on the coding side, there's a great question here. How do you keep the codes viable and not become obsolete? There's this idea of self-bootstrapping codes. Can you actually encode information in a way that to future, let's say, if there's interrupting civilization on Earth, and then you have to just start over again, there'll be something that's going to look like a puzzle that if you solve that puzzle, you would get closer to what the coding means. A giant Sudoku, could you turn storage or coding to a Sudoku that future generations could solve and figure out how you've encoded information, right? So that's how those self-bootstrapping codes do that. So let me see what else. I do think that this idea of breaking down the granularity of near data processing down to an extreme, I think is interesting. That with near data processing has been around for a long time. I know this community looks a lot at coupling processing with Flash, for example. But let's just keep breaking that down. What if you had a tiny little processor that did something very, very simple, and the data that it can operate on is very, very small, say a kilobyte? How would you organize storage and data structures that have active functions when the granularity of compute to storage is that fine, right? So think about ideas like that. I think would be great because we can start implementing some of those even in molecular forms today. Does that give you some ideas? Or
Yeah, I think that's great. I think many students are now writing down, taking notes and looking for their next research topic. Um, if I ask the
sounds
same
good. And please
question,
do reach out to us.
if I ask the same question from the biology side, do you have a wish list of things that you wish that they'd solve for this vision to come closer to reality?
Um, yeah, that's a great question. So we've learned a ton about how things actually work in molecular biology practices today, right? So let me give you one example. It might sound silly, but it's actually, I think, super important, right? So if you are debugging, if you're debugging an electronic circuit today or a program, you have really good tools to see the signal is off. It's very easy for you to observe stuff, right? So when things are broken, you can look at a core dump, or if there's a circuit, you can see that a wire is broken or something is overheating and so on. But now in molecular biology, typically mixing a clear liquid into another clear liquid, and a lot of stuff happens. It's highly non-deterministic, it's highly stochastic, and you don't have nearly the same visibility. Therefore, the protocols, the way they've been written for a long time, have been like for humans to read, and um, there's no clear, like well-defined, very semantically well-defined debugging processes that you bake into your what we call protocols, which is a equivalent of a program in a wet lab, right? So my wish list is that for biologists to embrace more and more, defining protocols in a very semantically unambiguous way with built-in, self checks, so that every step, something might have gone wrong or not. Now that's sort of like one at a high level. fundamentally, I think understanding more and more and exploring um, the functions of these fantastic proteins that we have. I mean, we just barely started scratching the surface of figuring out what proteins do, right? We understand the major ones, but we keep finding all sorts of new functions in proteins. And now we're having the ability of designing them. And proteins are incredible nanoscale robots that can process information in molecular form. And I think the progress that molecular biologists and biochemists are making there are fantastic. And my wish list for them is just that keep it accessible to computer scientists and make it accessible such that we can explore our ideas there. So
That's great. I think that since Karin was following all the questions, let her highlight if she thinks that any of the questions here are worth elaborating on a little bit more. I think that would be great because she probably
you see,
knows that better than me because she knows the answers.
yeah,
And
I know she's in the other room now. So let's see.
oh,
I
okay.
I can I'm actually looking at my phone here. So if there's any other questions that you think I should oh, there's a question about microfluidics platform, Opentrons. Yeah, so Alex Sharp. Yeah, so we do have Opentrons in our lab. In fact, our language can, there's a path from our Puddle language to Opentrons. Opentrons are bigger, for bigger bigger protocols, bigger volumes. The thing is, they're very useful and they have their place. But what we want to do is just shrink that down. Think of shrinking what an Opentron can do, something that fits in the Opentron is the size of say a dorm fridge. Okay. So shrink that down to a matchbox. And the nice thing is that now, since it's cubic, now I can probably put on the order of 500 to 1,000 units of a purple drop if you shrink it down compared to the volume of an Opentron. And that creates increased parallelism by a significant degree, and they serve slightly different functions, but I think the key here is how do you combine both of them. So let me see if there's any other here.
Well, there was a question at the beginning that got some attention. I think that for us, we're used to bits and transistors, and some of us are afraid of biological material. And there were questions about bad things that could
Yeah.
happen with DNA. Perhaps you can relate to that.
Yeah, no, I think this is a fantastic question, and trust us, we think a lot about this, and in fact, I ran DARPA set workshops on cyber biosecurity. It's not just biosecurity, not just cybersecurity, but the interaction of cyber and bio. For example, I think somebody was suggesting on like, oh, can you actually be clever and encode something in digital form that knowing the encoder is going to be a very harmful DNA sequence? Yes, I had to think about that. So that's why we put safeguards in place. The most fundamental safeguard specifically on DNA data storage is the fact that the DNA molecule that we store, each block size is very small. Okay, so think of it 150 bases. That's the unit of our physical storage. To put it in perspective, think about the COVID virus is, I think, just about 3,000 bases. Okay, so much longer because it has to code something much more complex. Like if you think about the proteins that are encoded, that can be encoded in 150 bases, they're very limited, unlikely to do anything, really anything meaningful, to the point where below a certain number, I think below 500 bases or so, the kind of DNA that we can manipulate can be done in a very low biosafety environment because it's just not harmful. Now, the other thing is, as the central dogma is that you go from DNA to RNA to proteins, right? So there's some little table that nature follows to make proteins out of DNA. And that coding is completely sent out of whack because the way we encode it is all random. It's not going to look like any meaningful protein. Does that make sense? And we can actually, because we randomize the data to begin with, it's even if you do code for a small protein, it's unlikely to do anything useful because it's going to look like random, right? So,
Thank you. So I think we have
but
time
yeah,
for
it's important to think about it. But yeah, go ahead. Yeah.
I think we have time for one last question. Um, and so there were several questions here about just using only the basic proteins that we currently have in DNA, or perhaps expanding, just using the same method to use more proteins.
Oh, yeah, I see. Oh, the base is not protein, the nucleotides, right? Yeah. Great question. So there's ACGTs. That's what we have, right? So that's what's evolved by nature. In fact, there are more synthetic bases that were designed. But the question is why. In fact, I could live with fewer bases because we're all computer scientists here. Like if you think about it, for you to increase the density linearly, you need an exponentially larger number of bases to increase density. right? Because you're going to put more symbols in a given physical position, you have more bits. You have to increase the number of different bases exponentially, which just now you have a system that's going to have 100 million bottles to have the DNA. It's just not going to work, right? I want to live with fewer bases, but it doesn't mean that synthetic bases wouldn't be helpful. What I do think it could be helpful would be designing bases that are easier to read and write. That I think makes sense. So basically, I do love the idea of fully synthetic bases. Um, but not because they're going to increase density, but because they're going to have better read-write properties. For example, the nanopore sequences that Karin talked about, if the bases look very different, the signal could look very different and easier to decode, right? So in that case, I think it makes sense to think about alien bases. And we have a bunch of thoughts on this, and I can point to papers on that too. So
That's great. So thank you very
okay,
much. Thank you both. It would be great if you can continue answering. I think
of course.
we'll have some more questions in the following minutes. People are still asking questions, so it would be great if you can come back and answer them. Thank you for joining us.